In my Internet introduction video, I introduced the idea of packet switching and the format of the Ethernet and IP packets. I also described the idea of layering of network services and protocols. Now, the Internet packet, or the network layer, carries higher level protocols, and the most important of these is the Transmission Control Protocol, or TCP, also called TCP/IP. This provides a reliable stream using sequence numbers in the packet and requesting retransmission for lost packets, and so on. And I talked about TCP/IP in that previous video. But there are two other very important protocols that I will talk about that are carried inside Internet packets. The first is the User Datagram Protocol, or UDP. It's a simple short message type protocol that offers no guarantees of delivery unless you embed a higher level protocol layer. Now, the network's pretty reliable, and most of the time, nearly all the time in fact, your UDP packet will get through. However, if you really wanted to guarantee delivery, then you'd have to have some higher level mechanism in order to get that guarantee. The second protocol I'll talk about is the Internet Control Message Protocol, or ICMP. And that's a protocol for exchanging control messages about the Internet itself. It's for controlling congestion and things like that. Now back to UDP. UDP is still really useful, and it's used for a number of services because it has a lot less overhead than TCP/IP. You don't need to actually establish any session or manage it or guarantee delivery or reassemble protocols or all those things. But there are situations where you don't need all that, and you'd like to get the low overhead. So I'll give you some examples of UDP later in the video. ICMP, the Internet Control Message Protocol, it provides messages that indicate status of connections or services, and also provides control messages that ask nodes to carry out network actions. ICMP is carried inside network packets, and so it's at the network layer of the protocol stack. Now, an example of a service provided by ICMP is a simple echo request, where the destination simply sends the ICMP packet back to the source. And this is used in the ping command, which you might have heard about. It's available on most systems, which you can use to test if a remote host is alive, is responding. It sends out the ICMP packet, which simply bounces back, is echoed back to the source. And so you can tell if it's actually operating. Now, an ICMP message has a time to live field. It's not actually a time, it's actually a number of hops. And this can be set on an echo message, one of these ICMP echo messages. And when the number of hops is reached, the intermediate node sends the message back to the source with an indication that the time, or the hop count, had been exceeded. Now, we can use this to find the route through a network using a process we call traceroute. There's actually a command to let you do this, to use this facility. So the way it works is that it sends out a message towards the destination, but only with a hop count of 1. And you can see that that hop count will be exceeded immediately that it gets to the first node in the path, the first router. And it will return that, and so you'll know what the first router is. Then you increase that hop count to 2, and you send out the message again. And once again, after 2 hops, the hop count will be exceeded, and that intermediate node will return the message, and so on. And you can do this for 3 hops now. In this case, hop count exceeded. You've worked out what the 3 nodes are in the link, until finally you get to the destination machine, and you get the message back to say that it's arrived there. And so you'll now know the IP addresses of the routers in the route to the destination. Now, Internet packets are transported through the network hop by hop to their destination, and each packet has an IP address. And as we saw in the previous video, it's a 32-bit or 4-byte number, And we usually write these down as 4 decimal numbers in the range 0 to 255, separated by dots. For example, 129.78.8.1. So that's an IP address. Now the IP address is used to decide how to get the packet to the destination. And there are 2 major classes of routing: local area networks and wide area networks. And I'll talk about each of these now. Now, a local area network is usually a broadcast network on a shared medium. And a good example of this is Wi-Fi. Every node on the network can hear the packets sent by all the other nodes. Now, there may be many conversations going on at the same time over the Wi-Fi, and it would be very inefficient if every time a node received one of these many packets, it had to decode it, since most of them are not coming to that particular node. They're going somewhere else. Only the ones that are really destined for your node need to be decoded. All you would do then is just discard them. Nodes usually only decode packets that have their specific Ethernet address as the destination address in the Ethernet frame. The problem is, on a broadcast local area network, how do you find out what the destination Ethernet address of another node? You might know their IP address, but you don't know their Ethernet address. The way you do this is, in addition to decoding packets that are sent to its own Ethernet address, a node will also decode packets sent to a special broadcast address. And in Ethernet packets or frames, the broadcast address consists of an address of all ones. Every bit in the address is set to 1. Now, to find out what the Ethernet address is that corresponds to a given IP address, we use a protocol, which is a particular packet format that's carried by the Ethernet frame, and we use that inside the Ethernet frame. And this protocol is called the Address Resolution Protocol, or shortened to ARP, ARP. If a node wants to find out the Ethernet address of a node with, say, IP address 23.234.1.1, it'll send out an ARP message to the Ethernet broadcast address that says, who has 123.234.1.1. The target node will hear that message on the broadcast address and decode it, realize it's an ARP message, and reply with a message directly to the source node, since you know the source node Ethernet address, since it was in the message, and so you'll discover what the Ethernet address is for that target. ARP messages are sent inside Ethernet frames, and so logically we think of them as something at the network layer. But what if the required destination is outside the LAN or the local area network? How do you know, for a start, how do you know it's outside the LAN? How do you know it's just not on your local Wi-Fi or your local area network? Now, the reason is that all nodes inside a LAN have an IP address chosen from a contiguous range. This range is always a block starting with the right-hand bit set to 0. And the first node, therefore, in this address block has address 1 as the last bit in the address. So a typical block would be 256 addresses long. So for example, 192.168.8.0 to 192.168.8.255. That's a range of 256. And all the addresses in that block would be found inside this local area network. And to test if a node address is inside this local area network, you simply use a logical mask. This is where you use the AND operation, and you use a mask, in this case, which is all ones except for the last 8 bits, which is 0. So in IP address notation, it would be 255.255.255.0. And you use the logical AND operation with the node address. So we start off with, let's say we're given the address 192.168.8.123. We want to see if that's inside our range of, or our net mask of 192.168.8.0. So what we do is we AND it, use the logical AND operation with 255.255.255.0. And in this case, we get back this number 192.168.8.0, which is what we were looking for. So we know that that address, the original address I had there with 123 on the end, is inside the local area network. Now, how do we? What if we have an address which is outside the network? Let's say this one, 192.168.11.123. This time, if we AND it with the mask, we'll end up with a number which is not equal to the LAN address of 192.168.8.0, and therefore we know that it's outside the local area network. Now, what do we do if we want to send a message to something which is outside the local area network? Well, in that case, we have configured a special gateway address that's inside our local area network, so we can send a packet to it, but it will then forward on the message to somewhere else. Basically, the idea is you say, I don't know who this is, you handle it. So it's something like this. So here we have the broader internet, and we have the gateway router, which in this case, the general convention is that it's the address 1 in your local area network. And so a packet coming from that address 5 in the local area network will be sent out through the gateway, and the gateway will then forward it into the internet. And while inside the local area network we might have Wi-Fi or a network switch or whatever, the connection to the internet might be something like an optical fiber or a DSL connection or something like that. Now we can generalize this with a routing table, and you can find out what the routing table is in a Unix system with the route command. So if I type that into my user interface, my command line, I will get something like this. And you can see in this case that anything inside the 192.168.87.0 network is sent locally out on the interface ETH0 in this case. But if it's not inside the network, we go to that default address, which is the router, which is the gateway, 192.168.87.1, and it will send it directly there. And that's how we do the routing to go outside the local area network. Of course, if you don't know the Ethernet address of the gateway router, you can very easily find that out using the ARP protocol. Now, we don't have to do this every time because your system will keep a list of known Ethernet addresses that it's discovered using ARP in the past, and it doesn't have to do it more than once because IP addresses and the corresponding Ethernet address don't change very often. Routing outside the local area network in general is also done with routing tables like this, telling you where to send things. But it's a little different because these tables are maintained by things called edge systems, which talk to each other with another protocol, not ARP in this case, but with another protocol such as something called BGP or Border Gateway Protocol. This is by far the most widely used wide area network routing protocol. And what that does is it exchanges information about the routes in the network. Now, I'm not going to go into detail in this video on BGP, it's really outside the scope, but basically the idea is that the whole IP address range, all IP addresses, are divided into blocks called autonomous systems, or AS. And information about each AS, what IP addresses are in it basically, but other administrative information, is then exchanged between the routers using this BGP protocol. And each wide area network router maintains a routing table containing the AS information. The wide area network router looks at the IP address, determines what the autonomous system or AS is that it's in, and then uses the routing table to decide where to send it to next, possibly another router in the path. Now, in 2021, which is the latest figures that I have, there were over 100,000 ASs on the internet. IP addresses, autonomous system numbers, and many other related numbers and names in the internet are all managed by an organization called the Internet Assigned Numbers Authority, or IANA for short. And most of the time, IANA is responsible for top-level allocation of numbers, but often it delegates the lower-level allocation to regional organizations. So, for example, it might divide up the IP address range into blocks, which are then given to regional registrars to allocate further. In the case of, for example, the Asia-Pacific region, IP addresses are allocated by the Australia Pacific Network Information Centre, or APNIC, located in Brisbane, Australia. I'm going to say a lot more about addresses and names and so on in the Internet protocols in a later video on the general area of namespaces. But an important aspect of addressing that I need to introduce in this video is the idea of a port number. Now, while IP addresses designate a particular computer on the local network, there is another level of addressing associated with IP addresses. And this is a 16-bit number that designates a service within the computer. So we have our IP address, but also there's this additional 16-bit port number. Here's an example. If we have a fairly typical IP address of 123.234.12.2, and in addition to that, we have a port number. In this case, it's a low number 80, which is the port number allocated to the HTTP service. That's the protocol for sending web pages around the network. A 16-bit port number allows 65,536 different ports or services. Some of these numbers are used for commonly used services, such as HTTP, and some are available for other people to use. Now, they're all allocated, they're registered and allocated with the Internet Assigned Numbers Authority. There's also a range of port numbers that, as I said, anyone can use. Now, common port numbers that are registered include 80 for HTTP and 25 for SMTP, which is the Email Transport Protocol. I've spoken about the media access or Ethernet addresses before and described how they are globally unique. Now, they're not managed by the IANA, they're managed by the IEEE, the Institute of Electrical and Electronic Engineers, and they are allocated to device manufacturers for the hardware they make. So each Ethernet interface that is manufactured has a unique 48-bit address when it leaves the factory. There's no need to configure anything when you get your computer. But what about the next layer, the network layer, where we have these 32-bit IP addresses? How do I find out about the IP address for my computer? Well, this could be done manually by putting the allocated number into a table when you start your computer or into an interface. But a better way is to have the gateway router maintain this list of IP addresses and either dynamically allocate them or statically decide which machine gets which IP address. But it does this using something called the Dynamic Host Configuration Protocol, or DHCP. The DHCP protocol operates at the IP layer using the UDP protocol that I mentioned earlier. Here is an example of using UDP for a higher level service. And DHCP operates with the IP broadcast address of all ones, so 255.255.255.255, and also the all ones broadcast layer at the Ethernet frame level. So there's an interchange of messages and an IP address is assigned and allocated to the client. We use the term leased to the client. This means that the client is only allowed to use the address for a limited time and has to periodically renew the lease of the IP address. This allows IP addresses in the local network to be reused if a client goes away. Here is an example network interface configuration window from the Apple Macintosh. You can see that it says that IPv4 is configured with DHCP. It shows the IP address and the mask, which I talked about earlier to show the range of local area network addresses. It shows the address of the gateway router that connects the local area network to the internet. And it also has a button where you can renew the address, the DHCP address, manually. Now, you don't have to do this normally because the Macintosh system will automatically renew when the time is up and it has to go through that lease renewal process. So in this video, I've introduced the low-level IP-level protocols in the Internet Protocol Suite, and I've covered the User Datagram Protocol, or UDP, the Internet Control Message Protocol, or ICMP. I mentioned the ping and traceroute commands and how they work using the ICMP protocol. I talked about routing in the local area network and the wide area network and the difference between these and how it generally works. I've talked about IPv4 addresses and the address resolution protocol of ARP, and also lastly talked about the dynamic host configuration protocol, DHCP. So thanks for watching.